Hello again. This is video lecture 22.5, and we have one more section in chapter 22 to talk about. And this is section 7 in chapter 22, where we're going to look at what happens to an electric dipole in an external electric field. So let me add a couple of adjectives to this section title. An electric dipole in an external electric field. Now remember what we mean by an electric dipole. 2-point particles with equal but opposite charge. There's a plus q and a minus q, and those two charges are separated by some distance d. That structure is called an electric dipole. And we want to know what happens when you immerse that electric dipole in an electric field that was already there due to other charges. Okay? That's what we mean by an external electric field. There are some other charges around, and they're creating electric field. We call that an external electric field. And into that external electric field that's already there, we're immersing this electric dipole. And we want to know, basically, what will the electric dipole do? How will it move? Okay? Now, this turns out to be more important than just an academic exercise, because there's a very important application, technological application, that uses the physics of what we're talking about here, the motion of an electric dipole in an external electric field. And that application is your microwave oven and how it cooks your food. Okay? So we'll come back to that. But I just want to motivate for you that there's our practical applications for what we're about to talk about. All right, so look first in what I've got here on the schematic picture on the right-hand side. We've got the plus charged particle, plus q, and then there's the negatively charged particle, negative q, and they are separated just by some distance d. That is the electric dipole. We'll take the 2-point charges to be identical, so the point right in the middle there on the line D is the center of mass of the dipole. Remember that point from last semester? The center of mass point is the most important point on a multi-particle system. Center of mass for this dipole is right there in the middle of that distance D. And the dipole has an electric dipole moment, little p arrow, that would be directed away from the negative charge and towards the positive charge. Okay, so that's the little p arrow right there, pointing away from the negative charge and towards the positive charge. Now this dipole has been, at the moment this drawing is made, immersed in an external electric field from some other charges that we're not even showing. We just want to know about that field, that external electric field. To make the whole situation here as straightforward as possible, the authors are assuming that this external electric field is uniform, spatially uniform, the same throughout this whole region of space. And the electric field lines that you see here in blue, which are directed, pointing from left to right, and uniformly spaced, are showing you that that uniform external electric field, E arrow, points to the right. And it's in that external electric field, E arrow, that the electric dipole, with its dipole moment, little p arrow, is immersed. And in fact, now they have a simplified picture right below, in which the two important vectors, the dipole moment, p, and the external electric field, E, are drawn with a common tail, tail to tail. Okay. Now the contention is that what this dipole will do when we put it in this field, let's say we put it in this field exactly like this with this configuration that you see, so that there is some angle theta right here between the dipole moment and the electric field. It's also right here. Same theta. Okay? What will the dipole do? Well, let's look at the pictures here. There will be a charge, a force on the positive charge. There'll be an F electric on the positive charge, and that will be, just using F equals QE, that force on the positive charge will be in the same direction as the electric field, and that force is right here, to the right. Okay, now that's the electric force on the positive charge. Same direction as the electric field it's in. But the negative charge down below, do F equals QE to get the force on that, but that's a negative Q. So the force on the negative charge is opposite to E. That way. They call it negative F because it's just the opposite of the F up above. And those F's have equal magnitudes. Do you see how we know that? F equals QE. They're in the same E, and their Q's have equal magnitude, just opposite sign. So this force up here on the positive charge and this force down here on the negative charge are exactly equal and opposite. So what's the net electric force on the dipole? 0, right? F net on the dipole is 0. That tells me that the center of mass will not move. Assuming it was at rest when I put it there, it will not move. Technically, it will not accelerate. But if I put it there at rest, which means its velocity will be constant, then its velocity will remain 0. The center of mass of this dipole isn't going to move if the electric field is uniform, which is what we're assuming. So I know already that when I plop this dipole down in this uniform external field, even though the dipole moment is angled relative to the field, the center of mass of the dipole is not going to move. So the dipole is not going to have its center of mass translating around. But the dipole is going to do something. You see what it's going to do? Did you say it's going to rotate? It's going to rotate about an axis through the center of mass. And I can see that by thinking about there being an axis through the center of mass perpendicular to the screen. I'll draw that axis right there in red coming out towards you. This upper force on the positive charge is going to want to make the dipole rotate that way about the axis through the center of mass. And the negative charge is going to want to make it rotate that way, but that's the same sense, right? It's going to want to rotate, as we look at it right here, clockwise. At least for the picture we're showing you right here. It's going to want to rotate clockwise. So the key thing I want you to see from the picture right now is that there is a tendency for this dipole, drawn like this, to rotate about an axis through its center of mass. And remember, the tendency of forces to cause rotation is called torque. And so the key point is that there will be a torque on this electric dipole in this uniform external electric field. And it's possible to calculate that torque. Now, I'm not, because of the sake of time, I'm not going to go through all those steps. Doesn't mean you have to take me on faith for that. If you want to see the derivation of this formula, then read section 22.7. They just start with the definition of torque. Note the symbol is the Greek lowercase letter tau as R cross F, where R is a position vector that points out from, in this case, the center of mass, to the place where the force is. And then you have to do that thing called a vector product or cross product. Remember that? So they start with R cross F, and they do that for the top F on the plus charge and the bottom F on the negative charge. And they combine them to get a total. And then when they do, what they get is a formula. And that's this formula right here in the middle. And that's the important formula that we have to use, because it will enable us to calculate the torque on an electric dipole in an external electric field. And starting with R cross F, the basic definition of torque from a force from last semester, it perhaps is not surprising that in this case for our dipole, our torque formula has a cross product, a vector product in it. Except what you get now for the dipole is take the electric dipole moment, P arrow, and take the cross product of it with the external electric field, capital E, P cross E, to get the torque on the electric dipole in this uniform external electric field. All right, so let's go back down now. So I'm telling you that that's the expression, okay? And that's what we will use to calculate torque. The bigger the torque, the bigger the tendency for the dipole to rotate about an axis perpendicular to the screen and through the center of mass. P cross E. That's the formula for calculating the torque on the dipole. Let's now just talk about the consequences of using that formula. So now I want to focus down here on the simplified picture that I talked about a moment ago. That shows the dipole moment vector, P in green, and the electric field vector, E, kind of in a gold color, and they're drawn with a common tail, so that you can also see the angle theta right there between them. All right, and so if we now are going to use this formula to get the torque on the dipole in the electric field E, we're going to use P cross E. We have to remember what we learned last semester about vector product of two vectors, or cross product. The resultant is another vector. That's the torque vector, tau arrow, and it's got a magnitude and a direction. We have to be able to get both. And to get the magnitude, we will do this the same way we would get the magnitude of a cross product last semester. Remember, our cross product here is P cross E. To get the magnitude of that torque, we will do the magnitude of the first vector in the cross product, little p, the dipole moment, times the magnitude of the electric field, E, times the sine of theta, where theta is the angle between P and E when they're drawn with a common tail. That's the theta right here in our drawing. And the theta can range between 0, that would mean P and E are exactly aligned, all the way to 180, where P and E are exactly opposite. That's the range of theta. Okay? Then there's a direction for this torque. And to get that, we use what's called the right-hand rule. So remember, when we take a cross product of two vectors, like this, P cross E, here's some things to note about the direction of the torque, or the resultant. First of all, any two vectors drawn with a common tail form a mathematical plane, flat surface. In our case, P and E are in the plane of the screen. And when you take the cross product of two vectors, the resultant vector, in this case torque, must be perpendicular to the plane of the original two vectors. Our original two vectors, P and E, are in the plane of the screen, so the torque on our dipole, that vector, must be perpendicular to the plane of the screen. Well, that only leaves you two options: straight out of the screen towards us, or straight into the screen away from us. And we only have to determine which of those two possibilities is the correct one. And the way you do that is with the right-hand rule. So remember, I used to use like two pens. I like to use the two-pen approach to doing the right-hand rule. I'll use the green pen for the dipole moment. I don't have a gold pen, so I'll use a red pen for the electric field. I hold them with the fingers of my left hand, because I need my right hand for the right-hand rule, and I hold them with a common tail in the configuration that they are as they're drawn on the screen. So for me, as I look at it, the E, the red pen, points to the right, and the P points up and to the right. And then take my right hand with my thumb out extended like I'm going to hitchhike. I've got to reach in with the fingers of my right hand so as to push P on top of E. First vector on top of second. P on top of E. Green pen on top of red. So I have to reach in this way because I got to push green down like that, but with the fingers of my right hand, like so. And when I do that, my thumb points away from me, which means into the screen. And you'll notice that's how they've denoted it here. They've denoted an X inside a circle. That's supposed to represent an arrow going away from you, the feathered end of the arrow. But the point is that the direction of the torque vector for this configuration is into the screen. Basically, curl your fingers of your right hand the way this thing wants to rotate and see which way your thumb points. This thing wants to rotate, this dipole moment wants to rotate clockwise as I look at it for this configuration. I curl my fingers clockwise, my thumb points away from me. All right, now let's ask a couple of questions, mini questions for practice. Here's the first one. What angle theta between the dipole moment and the external electric field E gives you a torque of 0, no torque, no tendency to rotate? Meaning if I put the dipole in the field at that value of theta and let go, it wouldn't do anything at all. What theta would do that? I'm letting you think about that a minute while I erase my screen here. Okay, so the question is, I'll write it over here to the side. What value of theta, remember that's the angle between the dipole moment P and the electric field E, gives minimum torque magnitude? Well, the minimum of the magnitude of something can be is 0. What value of theta gives 0 torque? See how to tell? Use that part right there in the magnitude formula, sine theta. What values of theta have sine theta equal to 0? There are actually 2. Theta could be 0 degrees or up to 180. So what would the configurations be in these two cases? For 0 degrees, the P and the E are exactly in the same direction. You put the dipole oriented like that in that field, and you will get no rotation at all. But another possibility is to have the P exactly opposite to the E, with a 180-degree angle between them. You put the dipole moment in the field like that, you have to do this one very carefully and let go, don't give it any kind of push, and it will stay like that. It will not rotate. Here's another question. What angle, theta, between P and E gives you the largest torque magnitude, the largest tendency to rotate? So what's the theta for max torque? What do you think about that? Did you say 90 degrees, right? Based on sine theta. Sine theta is a maximum when theta is 90. So that would mean the greatest tendency to rotate is when the dipole moment, say, is like that, and the external field it's in is like that. That'll give you the biggest tendency to rotate. Okay? All right, I'll ask one more little mini practice question for you. How should I change this picture right down here redraw it so as to get a torque on the dipole that is directed out of the screen towards us? Don't change E, change the P, change the direction of P. How must you do that to give a torque on the dipole that's directed not into the screen but out? Okay, letting you think about that. I'll come down here. I'm going to draw the picture. There's the E. Which way should we draw the dipole moment vector? Did you say anywhere below? I'll draw it like that. The angle value itself is not crucial there. Just that the theta is below the not the theta, well, yes, but the dipole moment P is below the electric field. Because then when you do the right-hand roll, the E's like this and your P's down here. And with the fingers of your right hand, you got to do this and your thumb points towards you. So then you have, and you can see that it's going to be counterclockwise rotation. Your torque vector, which will be coming straight out of the screen towards you, will be drawn as an encircled dot. All right, so a torque and a dipole in an external electric field can exhibit a torque and have a tendency to rotate. Now there's something else that goes along with the dipole in the external electric field. We know from the torque argument that it will tend to just sit nicely for us and not rotate at all if the dipole moment and the electric field are exactly lined up like that. So if I put the dipole in the field like that and just let go, it's going to stay. And it turns out that if I want that dipole moment to be at a different angle than that, if I want it to be more like that, not exactly lined up with the electric field, but at some angle, I'm going to have to reach in when the P is lined up with E and myself actually rotate it to the way I want it, which means I have to do work on the dipole to get it to look like this. And if I have to do work on the dipole, much like I have to do work to stretch a spring, this system is gaining what we call potential energy. Remember stretched springs? Same kind of idea. If I want the dipole to be oriented like that, not lined up with the electric field, I'm going to have to reach in and rotate it myself. I'm going to have to do work analogous to stretching a spring. And so there is potential energy of an electric dipole in an external electric field. And I'm just going to tell you what that formula is. If you don't need to take me on faith, you can read the derivation in section 22.7. Okay? I'm just going to tell you what the formula is for the potential energy of a dipole in an external field. And it's this formula right here. Remember the symbol for potential energy, U? It's negative. And now it's still going to include the dipole moment vector P and the electric field vector E, but it's not a cross product now. In fact, it's a dot product or scalar product. See that big dot? Because the resultant, in this case potential energy, has to be a scalar. So now we take the dot product, of the dipole moment vector and the external electric field with a negative sign, negative P dot E. So I've drawn the picture down here again with the dipole moment vector P at some angle to the external electric field vector E, and that angle is called theta. So the potential energy of the dipole in this configuration is negative P dot E. Let's remember how we calculate dot or scalar product of two vectors. Okay, after the negative, you would put the magnitude of the first vector, dipole moment, times the magnitude of the second vector, external field, times the cosine of that angle theta between them. Cosine, not sine. And with that equation, you can calculate the potential energy of the dipole in the field. How much stored energy is there? So here's a couple of little mini questions. What value of theta gives the minimum potential energy of the dipole in the field? Think about that a minute. Feel free to pause the video if you want to think carefully, and then come back when you're ready. Okay, welcome back. This question's a little bit subtle. It can trip people up the first time because there's a tendency to think that the minimum value of U is 0. And that would be when theta is 90, right? Because of the cosine. But that's not the smallest this can be from this formula because it's got a negative sign in front of it. In fact, the minimum potential energy, U minimum, the absolute smallest you can get, is negative magnitude P magnitude E. Negative product of those two magnitudes. And that clearly occurs just from the behavior of the cosine function when theta equals 0. Ah, well, that actually makes sense now. So the minimum energy configuration is when P and E are lined up like that. Well, that's the one configuration where if I put it there and let go, it'll stay. It's not the only one, but it's the stable one. So I guess not surprisingly, that configuration where it will stay if I put it there is the lowest energy one. So now, what value of theta gives maximum U? So what value of theta gives maximum U? And what is that maximum U? Think about that for a moment. All right, did you say that the biggest energy you can get, just from this formula in front of us, is positive magnitude P times magnitude E? That's the absolute biggest. And what angle theta will give you that? You see? Look at the cosine. It's when theta is 180 degrees, with the P and the E exactly opposite. That's the highest energy configuration. So even though, if I'm very careful, I can insert the dipole with P and E exactly opposite, and there will be no torque, so there would be no tendency to rotate. But that's a very high energy configuration. And even with just the slightest little perturbation to it, it will rotate around to the 0 angle configuration. Okay? All right, so we do need to be able to calculate the torque on a dipole in an external electric field and the potential energy on a dipole in an external electric field. And I'm going to have a little class engagement exercise on Blackboard for you. But let me just give you a heads up. Because of time, we're not going to be doing anything in class on this topic. So this video is pretty important. Don't forget section 7 and chapter 22 for further information. But before I show you the class engagement, I want to show you a Wiley Plus animation of a dipole in an external field. And come back to that point I made at the beginning of the video about how the motion of the dipole in this situation has some practical applications. Now I know it's schematic, but let's try to explain what we're seeing here in this animation. What we have done in this animation is showing you a side view of a positively charged sheet, flat sheet or plate with positive charge, and then parallel to it and up here, a negatively charged flat sheet. And they actually have equal and opposite amounts of charge. It turns out that configuration, as we will be learning, creates a uniform electric field in the space between the plates. And I've drawn a couple of arrows here. Hover over them and maybe you'll be able to see, you may or may not. There's an E arrow there and an E arrow there. Those are just two representative arrows showing you the uniform electric field between the plates. And there's a dipole. The little blue disk is the positive charge, and the red disk is the negative charge, and those two together make up the dipole. And that little green arrow in the middle is the dipole moment, P arrow, which points away from the negative charge towards the positive charge. And the blue arrows show the electric force. There's the force on the positive charge, up, and the force on the negative charge, down. The center of mass of the dipole is right at the origin. All right, so in this configuration, when I start running it, can you see which way? First, can you see that the dipole has a torque on it, and therefore there'll be a tendency to rotate? Which way will it rotate? Clockwise or counterclockwise? Counterclockwise, right? This, in fact, is when the dipole moment P and the external electric field E are at 90 degrees. This is the maximum torque configuration, maximum torque magnitude. So it will definitely rotate counterclockwise. And it will keep rotating counterclockwise until the dipole's lined up with the field. Then the torque is 0. What do you think would happen at that moment? Well, there's a thought that since the torque is 0 and the tendency to rotate is 0, it will just stop. But remember, all this dipole in any object has inertia. or rotational inertia. And it can't just stop from finite motion to no motion instantaneously. So it will overshoot the zero torque configuration and go on to the other side. Okay? And at that point, the torque is back the other way. So then it'll start to slow down, stop for a second, and start to rotate back the other way. And if I don't have any mechanism to stop it, it will just keep oscillating like that. So let's run the animation and see it do that oscillation. Lined up, but now the other way. Stops, and then comes back. So the torque actually, given the way we released it initially, it oscillates. And in fact, I make a graph there of the torque, which has a z component only as a function of time. Looks a little bit sinusoidal. Not quite, okay? But it oscillates. It's this oscillatory behavior of the dipole in the external field that is getting at the important part of the way microwave ovens work. And in that case, they're obviously, when you put your food in the microwave oven, they're counting on the water molecules in the food, which have a dipole moment. And then when you start the microwave, you will end up creating what's called an electromagnetic field in there, which includes an electric part. And that will then give you a situation that's not vastly different from this picture. And that will cause the dipole to rotate, which will mean it'll have kinetic energy. And we learned in thermodynamics that the kinetic energy of the atoms and molecules is related to the temperature. So more kinetic energy, more temperature. You're heating up your food with the oscillations of the dipole moments of the water molecules in the field. Okay, so I just wanted you to see that motion kind of animated in time. All right, so there is just a little class engagement here to leave you with. Put that, you can answer that on Blackboard. And it goes like this. This figure shows 4 orientations of an electric dipole in an external electric field with the same value of the angle theta. But look carefully at the orientations. Here's dipole 1 with the plus charge up here and the negative charge down here, and they're showing you that this angle right here is called theta. Here's dipole 2 with the plus charge up here and the negative charge down here, and the angle theta that they're measuring this way is still theta. Still same as the other one. Dipole 3 is down here, plus charge there and the negative charge there, same theta. And dipole 4 is down here, with the plus charge there, the negative charge there, same theta. They're all immersed in this same electric field, E, which you can see, uniform field, points to the right. So you are to rank those 4 orientations according to the magnitude of the torque on the dipole, largest to smallest. Rank the torque magnitudes on the 4. Then, rank the orientations according to the potential energy of the dipole, largest to smallest. Okay? That's all you need to do. Just think about the things we just talked about on this video, and we will be returning to this physics of torque and potential energy of a dipole in an external field as we need it throughout the rest of the course. But that's all for this video.